Hello and welcome to ControllersTech. Let's say I want to perform multiple tasks where I need to read a sensor, update the display, and receive some data from the UART as well. If we use the regular superloop to do this, there are three main problems that we can face. First, Hall delay does not pause just one thing. It freezes the entire CPU. So while you're waiting 500 milliseconds for the display update, your UART may lose data and your sensor may miss readings. Second, multiple timing requirements start to conflict with each other. A 200, 500, or 1000 milliseconds delay does not compose cleanly in one loop. Third, any task that needs to wait without blocking the loop must become a complex state machine. The code becomes unreadable very quickly. The while loop works for one or two timing requirements, but after that you need something better. This is where an RTOS comes in. An RTOS, or real-time operating system, is a lightweight operating system designed for embedded systems. Its main job is scheduling, deciding which piece of your code runs and when. Instead of one loop doing everything, you write independent tasks, each focused on a single job. A sensor task, a display task, and a UART task. Each one looks like its own small program with its own infinite loop. The RTOS runs them all, switching between them thousands of times per second, so fast that they appear to run simultaneously. Today we will start a new video series on FreeRTOS. This series will be focused on implementing CMSIS-RTOS version 2, rather than using the native FreeRTOS APIs directly. Throughout this series, we will cover tasks, semaphores, mutexes, queues, task notifications, software timers, and much more. We will understand not only how to configure them in STM32 CubeMX, but also how they work internally and how to use them properly in real embedded projects. Before writing the code, you need to understand what a task actually is, because it is not just a function. A task is an independent program. It has its own stack, its own saved CPU registers, and its own program counter. When the RTOS pauses a task mid-execution, every register, every local variable, and every byte of its state is saved. When it resumes, it continues exactly from that point, as if it was never paused. Internally, the RTOS tracks every task using a task control block, TCB. It is basically a small data structure that stores the task's stack pointer, priority, current state, and timing information. The scheduler reads this to manage everything. This is why every task has its own infinite loop. If a task returns, it will be deleted by the RTOS. That is why we never want a task to return, so we create an infinite loop for it intentionally. There are mainly four states you will see for a task. The first one is running, which means the task currently owns the CPU. The ready state means the task wants to run and is waiting for the scheduler. Blocked means the task is waiting for a delay or a resource. It does not use any CPU at that point. Terminated means the task has been deleted. Basically, it is gone forever. The scheduler always picks the highest priority ready task. Blocked tasks are completely skipped. No CPU time is wasted on waiting. Now we understand what an RTOS is and what a task is. But the main question is, where does CMSIS-RTOS come into the picture? There are many RTOS in the embedded world: FreeRTOS, RTX5, ThreadX, Zephyr, and others. Each has its own API. Code written for FreeRTOS doesn't compile against RTX5 without rewriting everything. CMSIS-RTOS is an abstraction layer, a standardized API defined by ARM that sits on top of any compatible RTOS kernel. It does not schedule anything. It simply provides a consistent set of function names. For example, OS thread new calls X task create in the case of FreeRTOS. OS delay calls V task delay, and so on. This is how CMSIS-RTOS is arranged. On top, you have your application code, which calls the CMSIS-RTOS APIs. These then call the FreeRTOS or any other kernel APIs, which actually control the STM32 hardware. The benefit of using CMSIS-RTOS is that your application code becomes portable. If ST ships your project with FreeRTOS today and you switch to another kernel like ThreadX or RTX 5 tomorrow, your code will still call OS thread new. It will not change. Only the underlying kernel wrapper changes, while your application code remains exactly the same. Now that we have a basic idea of what an RTOS is, why it is used, and how CMSIS-RTOS acts as an abstraction layer on top of the native RTOS APIs, let's create a quick project in STM32 CubeMX to implement it. I am going to use the Nucleo L496 for this project. So let's start CubeMX and access the board selector. I am using the Nucleo L496 variant P, which is the 144-pin Nucleo board. Let's start the project. Do not start the peripherals in the default mode. Some of the pins are configured by default. Let me first clear all the pins so that we can build everything from scratch. We will start with the clock configuration. This Nucleo board does not have an external crystal for the system clock, so I am going to use the internal oscillator. Therefore, we will not enable the HSE or LSE clocks. Go to the Clock Configuration tab and set the source as the high-speed internal oscillator. We will use the PLL to run the system at the maximum possible 80 MHz. That is all we need here. Now go back to pin configuration. Go to sysdebug and enable serial wire debugging. This will help us debug the project when needed. Next, we will enable FreeRTOS. It is located inside the middleware section. Expand it, click on FreeRTOS, and enable CMSIS version 2. This is the newer version, so we will use it in this video series. There are many parameters available for configuration, but today we will keep things simple. I will explain only the few that are required for now, and as we proceed through the series, we will cover the others. The first one is the tick rate, which is set to 1000 Hz. A tick rate of 1000 Hz means the sys tick fires 1000 times per second, that is once every 1 millisecond. This gives us a 1 millisecond resolution. In FreeRTOS, this effectively allows us to create delays with a minimum resolution of 1 millisecond. Next is the minimal stack size, which is set to 128 words. This value is in words, not bytes. Since one word on a 32-bit Cortex-M is 4 bytes, 128 words equals 512 bytes. Each task in an RTOS has its own stack. The stack stores local variables, function calls, return addresses, and the CPU registers during context switching. When the scheduler switches tasks, it saves and restores data using this stack. If the stack size is too small, a stack overflow can occur, leading to unstable or unpredictable behavior. That is why a minimum stack size is defined, to ensure every task has enough memory to run safely. Next, look at the total heap size, which is currently set to around 3 kilobytes. All RTOS objects such as tasks, timers, semaphores, queues, and other kernel resources allocate memory from this heap. Whenever we create a new RTOS component, memory is taken from this shared heap space. As the project grows and more RTOS features are added, the heap requirement will increase, so we may need to adjust this value later. For now, since this is a simple project, we will keep it at 3000 bytes. Now go to Tasks and Queues, and you will see one default task already created. Double-click it to see its properties. The task name is default task. We do not use the task name in our code, it is only for identification. The priority is set to normal. If you expand the list, you will see many priority levels available. For now, we will keep it at normal. We will explore priorities more when we create multiple tasks. The stack size for this task is set to 128 words, which is the minimum allowed value. Even though the task is empty, this is the minimum stack size required. The entry function is start default task. This is the main task function where we will write our application code. It is automatically generated by CubeMX, and we will modify it later in CubeIDE. We are not passing any parameters to this task, so the argument is set to null. If needed, we could pass a pointer to data or configuration parameters here. The memory allocation is set to dynamic, which means the RTOS will automatically allocate the required memory, such as the task stack and control block, from the heap at runtime. If you check the FreeRTOS heap usage, you can see that 632 bytes are already used by the default task. Out of these, 512 bytes are allocated for the task stack. The remaining bytes are used by the task control block, and other internal RTOS structures required to manage the task. The rest of the heap memory is still available and can be used when we create additional tasks, queues, semaphores, or other RTOS objects. For this demonstration, I am going to blink one LED. The Nucleo L496 already has one onboard LED. From the schematic, we can see there is a blue LED connected to pin PB7. So we will configure PB7 as an output to control this LED. Go back to CubeMX and set PB7 as a GPIO output pin. That is all the configuration we need. Now go to Project Manager, give the project a name, I am calling it RTOS Part 1, and make sure the IDE is set to CubeIDE. Then click Generate Code. You may see two warnings. The first suggests not using SysTick as the default time base. The second suggests enabling the new LibReentrant option. Click No for now, and let's configure them properly. First, enable new LibReentrant in the FreeRTOS advanced settings. This ensures that standard C library functions like printf work safely in a multitasking environment. Next, go to Sys and change the time-base source from SysTick to a timer. We can use any of the available timers for the time base, but it is better to use timer 6 or timer 7. These are basic timers and do not have advanced features like input capture, output compare, or PWM. Since they are simple and usually unused in most projects, they are ideal for providing the HAL time base when working with FreeRTOS. That is all we need to change. Now click Generate Code, and you will see that the project is generated without any issues. Finally, import the project into CubeIDE. Locate the project folder generated by the CubeMX, and click Finish. Alright, the project has been imported to CubeIDE, and here you can see the main file of the project. The FreeRTOS files are located under middleware third-party FreeRTOS. Inside the main.c file, you will see the default task handle, and its attributes defined, exactly as we configured them in CubeMX. Such as the task name, stack size, and its priority. Here we have the entry function. As I mentioned earlier, this is the main task function where we will write our application code. This function will be defined later in the file, and we will add our task implementation inside it. Inside main function, after initializing the peripherals and clocks, the code calls OS kernel initialize. This function prepares the RTOS kernel before any tasks are created or started. It initializes the scheduler, internal data structures, and memory management so that tasks and other RTOS objects can be created safely. Then there is space for initializing mutexes, semaphores, timers, or queues, which we are not using right now. After that, the task is created using OS thread new. The parameters of this function are entry function of the task, the data to be passed to the task, and the thread attributes, which are already defined above. Finally, OS kernel start is called. This function starts the RTOS scheduler and begins multitasking. From this point onward, the scheduler takes control of the CPU and starts executing the created tasks based on their priority. After OS kernel start is executed, control does not return to main function. Any code written after this function call will not run, because the RTOS is now managing the system. Internally, OS kernel start calls vtask start scheduler, which is the native FreeRTOS API. Now scroll down and find the start default task function. Inside it, you will see a user code section and an infinite loop. The infinite loop ensures that the task never returns. If a task function exits, FreeRTOS will automatically delete that task. That is why every task must run inside an infinite loop. Inside this loop, we will blink the LED by calling hold GPIO right pin to set and reset pin PB7. For the delay, we will use OS delay to create a 1-second delay between setting and resetting the pin. This means the LED will turn on for 1 second and then off for 1 second. Now you may ask, how is this different from using HAL delay? HAL delay blocks the entire CPU until the delay is complete. Internally, it waits in a loop until the required time has passed. During this time, the CPU keeps checking and effectively wastes cycles doing nothing else. On the other hand, OS delay does not waste CPU cycles. It puts only the current task into the blocked state for the specified time. While this task is waiting, the scheduler is free to run other tasks. That is the key difference. HAL delay blocks the entire CPU, whereas OS delay blocks only the current task. Now build the project. There are no errors here, so let's flash the project to the board. You can see the blue LED blinking every 1 second. This confirms that a basic RTOS project is now set up and running successfully. We have configured FreeRTOS in CubeMX, generated the project, initialized the kernel, created a task using OS thread new, and started the scheduler using OS kernel start. The task is executing independently, and the LED is blinking using OS delay, which proves that the scheduler is managing the CPU correctly. At this point, you have understood the complete flow of a minimal RTOS-based project, from configuration to execution. You also saw the fundamental difference between a traditional superloop approach and an RTOS-based design. In a superloop, everything runs sequentially and blocking delays freeze the entire system. In contrast, an RTOS allows multiple tasks to coexist, and when one task is waiting, others can continue executing. This is the core advantage of using FreeRTOS in embedded systems. This foundation is very important because everything we build in the upcoming videos, semaphores, queues, mutexes, timers, notifications, will rely on this task and scheduler concept. That is it for today. You can download the complete project from the link in the description. If you have any doubts, leave them in the comments below. Keep watching, and have a nice day ahead.